Hello all, I am Siddharth Kaul and I welcome you to Edupedia world. In this video, I am going to talk about how to create and work with unit tests in your Matlab program and code.
The video has been divided into 9 sections. There are more sections that will be covered in the next video. To give you a brief, I will cover 3 things here. First is the script-based unit testing, second is the function-based unit testing, and third is the class-based unit testing.
In this first section, I am going to talk about how to write scripts that act as unit tests for your Matlab program. These scripts will test the function that you create. I will first start by creating the function I want to test. I have created a function right triangle that will take the input length of 2 sides of a triangle, will return the 3 angles of the corresponding right triangle. Here I will make sure that the input I provide will be the 2 shorter edges of the triangle and not the hypotenuse. The function looks something like shown on the code snippet here. So basically I am taking input sides, that is a numeric array of size 2 that contains the shorter sides of right angle triangle, and I will be outputting angles, that is again a numeric array, but here it will be of size 3, that will be all the 3 angles of the right triangle. Creating a test script. In my working folder I will create a new test script, right triangle test.m. I will give you this demonstration after this slide, but let me go through all the steps first. Here I will create unit tests, and each unit test will check a different output of the right triangle function. I have created this test script by following the convention shown here on the slide. First and foremost, I have ended my script with the word test. So to let Matlab know that this is a test script, you can start your script name with the test to have the same impact. Second thing I did is that I placed each unit test into a separate section of the script file. Each section begins with 2% signs, and the text that follows on the same line becomes the name of the test element. If no text follows the %2% sign, then Matlab assigns a name to the test. If Matlab encounters a failure, it still runs the remaining test. In a test script, the shared variable section consists of any code that appears before the first explicit code section, that is the first line beginning with $%. The test share the variables that I will define in this section. Within a test, I can modify the values of these variables. However, in subsequent tests, the value is reset to the value defined in the shared variables section. In the shared variables section, that is the first code section, I will define any precondition necessary for my test. If the inputs or outputs do not meet this precondition, Matlab will not run any of the tests. Matlab marks the test as failed and incomplete. When a script is run as a test, variables defined in one test are not accessible within another test unless they are defined in the shared variable section, that is the first code section. Similarly, variables defined in the other workspaces are not accessible to the other tests. If the script file does not include any code section, Matlab generates a single test element from all of the full contents from the script file. The name of the test element will be same as the name of the script file. In this case, if Matlab encounters a failed test, it halts the execution of the entire script. Now through demonstration, let me explain you these conventions and how my test script will look like and how my test script is actually looking.
Basically, it takes the input argument sides, which is a numeric array. The point to note here is the sides it takes is the length of sides, that is non-hypotenuse sides. This means this is the base, this is the height, but none of these are hypotenuse. So based on this, it will do a calculation for A, B and C, where A, B and C are the angles. And it will return these angles as a numeric array back to the calling function or to the command line. Now let us see the test script for the same. So this is the test script for it. So in this, I first defined the conditions, and then I've defined the precondition, and I segmented a test by using $% and writing the test name, that is test1 sum of angles. Then I have the second test, that is test for isosceles triangles. Then I have test 3, that is 30, 60, 90 triangle, and the test 4, that is a small angle approximation. So right now the test 3, that is the 30, 60, 90 triangle, and the test 4, small angle approximation triangle, these are the 2 test cases that will actually fail. because as these are floating point values, so there has to be some tolerance there has to be some tolerance inside it. So we will see about that later. So these are the four tests that I'm going to execute. So each test, as I discussed before, each test is marked with the double percentage sign, and the test description is written below. Again, the test title follows as is the isosceles triangle test, and the description follows below. I am using the assert functions to assert whether the condition is true or false. If the condition is true, Matlab will pass the test, and if the condition is false, the Matlab will fail the test. And one more thing, I'm going to run this test using the run test method. So basically what run test method do, as my file name ends with test, so it will recognize the script as a test based file. So basically all the subdivision, that is the double percentage sign, that run test function will divide them as number of functions. So each segment is a test case. So we have test case 1, test case 2, test case 3 and test case 4, and it will run through all the 4 tests. If say for example test 1 fails, then it will skip the test. So now let's run it. So I'm going to create a temporary variable, that is the results, and I'm going to run tests, and I'm going to pass this file name, that is the right triangle test. Again I will repeat that a script based testing file name should at least start or end with the keyword test. Then and only then this run test function will recognize it as a test file. Now I'm going to hit enter. It will run the test and it will give something output like shown here. So basically it error occurred, as I said, in 30, 60, 90 triangle test, that's the test 3, and it did not run to completion. This is because the assertion failed. Again, fourth test, that is a small angle approximation, it also did not run to completion, so it also failed. So basically these two test cases failed, and these both will be marked as incomplete. So let's go to the failure summary to see the same. So yes, as I said before, test 3 has failed, test 4 has failed, and they will also be marked as incomplete because assertion itself has failed. So this is how the run test. Oh yes, and one more thing, the result is basically a 1x4 array with properties of name, past, fail, incomplete and duration. We can look into all of these properties independently. The one more good thing about run test is also tell us about the time that has passed in testing this. So this is upon 0.16354 seconds that has Matlab taken to run all of these 4 tests. So we have the 2 past tests, that is test 1, test 2, 2 failed tests and 2 incomplete tests, that are test 3 and test 4. So let me now modify this test script file to add tolerance to test 3 and test 4, so that this also pass. So basically I created the same copy of right triangle tolerance test and I add tolerance to it. Now let us see like what is the difference here. So in the right triangle test, these are the, before the first double percentage, everything that I defined in the test script is shared among all the tests in the script. So all the conditions and all the preconditions can be accessed by all of the tests. So in the precondition, I added a tolerance value of 1e to the power -10. So here I defined an absolute tolerance. Now let us see in the original file how the test 3 and test 4 looked. So test 3, that is the 30, 60, 90 triangles, look something like this. The assertion was done based on absolute value, that is angle of 1 that was equal to 30, equal to 60 and equal to 90. Similarly in right triangle tolerance, in the test 3, you can see I have taken the absolute value, that is the angle 1 minus 30, and I have provided it with the tolerance of and I, instead of putting it equal to 30, I subtracted it with 30, and I will see whether it fits the tolerance. If it fits the tolerance, it means the angles are equal. Similarly I did for 60 and similarly I did for 90. Again for test 4, that is the small angle approximation, the assertion is that approximation should be equal to the smaller angle. So again, similar to what I did in test 3, I subtracted the approximation with the smaller angle and I compared it with the tolerance. If it is less than or equal to our tolerance, then basically our small angle and approximation is equal. So now let me rerun these tests. So I'm going to run test, that is results, run tests, and I'm going to pass this tolerance file, that is the right triangle tolerance test file. Again, I will emphasize that my test file name ends with test. You may start it with test or end with test, it's all up to you. Now I'm going to hit enter. As you can see, now all the 4 test cases have passed and there are 0 failure and 0 incomplete tests, and the time taken is close to this. As I'm repeatedly running these tests, so basically the Matlab will take less and less amount of time each time. So this is like a small, very simple demo on how to execute script based tests.
Typically, with script based test, you create a test file and pass the file name to the run test function without explicitly creating a suite of test objects. If you create an explicit test suite, there are additional features available in script based testing. These features include selecting tests and using plugins to customize the test runner. Here in the second section, I will talk about these extra additional features that are available with script based testing. One of the additional features of script based testing is creating test suite. To create a test suite from a script based test, you can use the from file method of test suite. Then you can use the run method instead of run test function to run the tests. For example, if you have a script based test in a file right triangle tolerance test, these two approaches that are shown in the code snippet on the slide are similar. First one is where I have passed the right triangle tolerance test to the run test function, and the second is creating an explicit test suite using the test suite function from the file as shown in the last, and then I will run the created suite. Both of these statements will produce the same result. You can create a test suite from all the test files in a specified folder using the testsuite.from folder method. If you know the name of a particular test in your script based test file, you can create a test suite from that test using the testsuite.from name. Another additional option that is available is test selection. With an explicit test suite, you can use selectors to refine your suite. Several of the selectors are applicable only for class-based tests, but you can select tests for your suite based on the test name. You can use the name value pair argument in a suite generation method such as from file. Here I have done the same by passing the name value of triangle. Then you can use a selectors instance and optional constraint instance. You can use these approaches in a suite generation method such as from file, or create a suite and filter it using testsuite.selectIf method. For example, in this listing, the 4 values of suite are equivalent. The first is a name value pair where test is selected using the name value pair, that is the name and triangle. The second is the selector, where you pass the selector as an argument and get the test. Again, the selector is basically based on the string that is triangle, so I am selecting the same test here also. Third is the select if name value pair, where test happens if match happens. So it's a the third one is based on select if method, where we pass the name value pair. Here the name value pair again is name triangle, and if we find the test in the file, then it will execute the same. And fourth is using the select if method with the selector as an argument. And the fourth one as shown here in the last is where I pass the selector in the select if, and if it exists, then the test will run. If you use one of the suite creation method with the selector or name value pair, the testing framework creates the filtered suite. If you use the testsuite.selectIf method, the testing framework creates a full test suite and then filters it. So for very large test suite, this approach can have some kind of performance implications. Another additional features for script-based testing is the test runner customization. Using a test runner object, you can customize the way framework runs as a test suite. With a test runner object, you can basically produce no output in the command window using the with no plugins method. You can actually run tests in parallel using the run in parallel method, and you can add plugins to the test runner using the add plugin method. So for example, I have used a test suite here. So I will create a silent test runner and run the test with the run method of with no plugins method of test runner. So running with no plugins, there will be no output that will be generated on the command window, and it will just execute on the background. Apart from script based testing, there is a function based unit testing. Basically, this test function in a single Matlab file that contains a main function and lot of individual local test function. Optionally, you can include file fixtures and fresh fixtures functions. File fixture consists of setup and teardown functions that is shared across all the tests in a file. These functions are executed once per test file. Fresh fixtures consist of setup and teardown functions that are executed before and after each local test function. As discussed briefly before, the function-based unit tests are very much similar to the script-based unit test. All tests are there in a single function file. This function file has a main function that collects all of the local test function into a test array. Since it is the main function, the function name corresponds to the name of your .m file and follows the naming convention of starting or ending in word test, which is case insensitive. In the sample shown on this slide, I have an example test function file with local function test function1 and function2 test. The main function needs to make a call to the function test to generate a test array. You can use local functions as the input to the function test to automatically generate a cell array of function handles to all the local functions in your file. This is a typical main function. Array of tests are created by using the function test and passing the argument local functions to it. This will automatically generate the test array. Individual test functions are included as local functions in the same Matlab file as the main function. These test function names must begin or end with the case insensitive word test. Each of the local test function must accept a single input, which is a function test case object test case. So basically, test function 1 will have an input argument of test case and function2 test will also have an input argument of test case. The unit test framework will automatically generate this object and pass it to them. So the function test function 1 and function2 test are the typical examples of it. So this is how our main function and its subtest functions will look. So in the first main function, that is example test, there is a function called to a function test and all parameter is passed, that is local function. Then the unit test framework will automatically create a test array for all the local functions in this main function file. Then I have two test functions. The one is test function 1, where I am passing the input argument of a test case, and in function2 test, where also I am passing the input argument of test case, that will be automatically handled by the unit test framework. In the same function file of example test, there is a choice to add optional fixture functions. Setup and teardown code, also referred to as test fixture functions, set up the pre-test state of the system and then returns it to the original state after running the test. There are two types of these functions. File fixture functions that runs once per test file and fresh fixture functions that run before and after each local test function. These functions are not required to generate tests. In general, it is preferable to use fresh fixtures over file fixtures to increase unit test encapsulation. Function test case object test case must be the only input to the file fixture and fresh fixture functions. The unit test framework automatically generates this object. The test case object is a means to pass information between the set of functions and test functions and also teardown functions. Its test data property is by default a structure which allows easy addition of fields and data. There are typical uses for this. Test data include paths and graphic handlers. You can use file fixtures functions to share setup and teardown functions across all the tests in a file. The names for the file fixture function must be set up once and teardown once respectively. These functions execute single time for each file. You can use file fixtures to set a path before testing and then reset the same path to the original path after testing. This is shown here on this slide is a typical example of skeleton of a file having a file fixture setup and teardown code. So basically the file fixture code are set up once and tear down once, and the fresh fixture code is set up and tear down, and all of them has an input argument of test case which is automatically passed on by the unit test framework.
Based test file looks like. So I have a function that is the example test, that is my master function. So this is basically a main function that I will use to generate tests. So I will call the function test and I will pass argument that is local functions. So basically it will create an array of tests. So all the local functions that have starting name or ending with test will be included in this. Now inside this same example test function file, I will have my test functions. So here I have test function 1 and function 2 test. Both of these functions will take test case object as an input argument. We do not have to worry about passing this object, as unit test framework will automatically take care of it. Inside these functions we will write a test specific code. This can be anything, whatever we want to test we can write it here. Then we have optional file fixtures. So basically these are the functions, that is the setup once and tear down once, that are called once for this entire file. So this will be called before starting all the tests, and this will be tear down once will be called when all the tests are completed. So this will set up the file for this will set up the environment for the whole file, and this will tear down the environment for the whole file. Similar to this, we have optional fresh fixtures. So basically setup and tear down functions are the fresh fixtures. So these are called before each of these local test functions. So before the test function 1 is called, the setup function will be called, and after the test function 1 has completed the execution, then the teardown function will be called. So basically it is used for each of the local functions. So these are the steps that we can repeatedly call, like opening a figure, closing a figure, opening a figure, closing a figure, something like that. So this is how the function based unit test file looks like.
Now when you run the test, this is how the flow happens. You start the test using the run test method, and it begins with creating a test array of all the local functions. After creating the test array, the setup is done for the file fixtures, and then a loop is done over all the test function, where for each test the fresh fixtures are performed. Then test is executed, and then the teardown function takes over to reset the fixtures, and process starts again till all the test functions have completed the execution. After this loop, the teardown file fixture function is called to reset the file fixture that was set up at the beginning, and then it comes out and tests are completed. Moving on, in this section I will provide first the explanation of what the code is about, and then I will give a short demo and unit testing using functions. Before moving to demo, let me explain to you part by part the code that is involved. First is the function that I am going to test. Here I have a quadratic solver function that takes three coefficient inputs a, b and c for the equation ax square plus bx plus c equal to 0 kind of equation. The code first checks the coefficient whether they are a number. If not, then it will generate an error and will terminate. If they are a number, it will go on finding the two roots of the equation and will return the numeric array roots to the calling function. Now I will create a second function file of solver test. This function using function test method will call all the local functions that will be defined in this file. A call to function test using local functions as input creates an array of tests from each local function in the solver test.m file. Each test is a local function that follows the naming convention of having test at the beginning or end of the function name. Local functions that do not follow this convention are not included in the test array. Test function must accept a single input argument into which the test framework passes a function test case object. The function uses this object for verification, assertions, assumptions, and fatal assertions. It contains a test data structure that allows data to be passed between setup, test, and teardown functions. Now I will create my first test function that will test the real solution of the quadratic equation. Now consider an equation like, say for example, x square minus 3x plus 2 equal to 0. The real solution for the same is x equal to 1 and x equal to 2. So my test real solution function will call the quadratic solver with the coefficient 1, minus 3 and 2, and I will be expecting a value of 1 and 2. If these are not equal, then the Matlab will say the test has failed. Next, I will be adding a function to test the imaginary solution. For this, consider the equation x square minus 2x plus 10 equal to 0. This has imaginary solution of x equal to minus 1 plus 3i and x equal to minus 1 minus 3i. I will use the verify method to know whether the expected solution and the actual solution matches or not. If it does not match, then Matlab will consider it as a failure. Now I will demonstrate this to you.
Unit testing. So first I'm going to close these script based files, and I'm going to open my function that I'm going to test. So basically I will be testing quadratic solver that will solve the equation of form ax square plus bx equal to 0. So as I already discussed, the first it will check whether the coefficient a, b and c are basically numeric or not. If it is not numeric, it will pass on an error, and then it will calculate roots and pass the roots back as a numeric array. Now for the same, I have written a test function file, that is solvertest.m. So solvertest is the main function under which we have all our sub-test functions. So in this, I am creating a test array by calling the function test and passing the local functions argument to it. Now I'm going to first write a test function for a real solution. So here, as I said, x square minus 3x plus 2 equal to 0 is the equation, and the expected real solutions are x equal to 1 and x equal to 2. So the test real solution function looks something like this. We have a test case object passed to it. This will be automatically taken care by the unit test framework. Now using the qualification method, that is the verify equal, I'm going to pass the argument of test case, the actual solution and the expected solution. So actual solution is something that I will get from the quadratic solver by passing these arguments. Expected solution is what I expect the function to return the argument. So when these both are equal, then verify equal will tell the Matlab that the test case has passed. Similarly, for imaginary function, imaginary solution, I have a function test imaginary solutions. Again, I pass test case object to it. I am getting the actual solution by calling the function and passing the arguments, passing the coefficients 1, 2 and 10. My expected solution is minus 1 plus 3i and minus 1 minus 3i. So again, using the verify equal qualification method, I am going to pass the test case object, actual solution, expected solution, and the function will tell the Matlab whether the test has passed or not. Now let us run this. I'm going to again create a results variable. I'm going to call the run test function, and I'm going to pass this solver test function file. So as you can see, it took 0.1 second to run the test, and all the two test cases have passed. So there are no failures and there are no incomplete tests. So this is like a small demonstration for a function based unit testing.
Now let's talk about setup and teardown functions. So there are two set of functions. One that creates a setup for whole file, and that is setup once method, and the second that creates setup just before calling the local function, that is the simple setup method. Similar to that, there are two teardown functions. The teardown once method, that is called once all the local functions are called at the end of the file, and the second is the simple teardown method that is called after each local function. This section will cover both of these and will give example for the same. For the sake of the example, I am going to create a file containing the main function that tests figure axis property. I will create two functions, two unit tests, one which will verify the x-axis limits if x-axis limits are correct, and the other that will verify that the face color of the surface is correct. So I will create the function file name axis properties test. In the main function of this file, Using the function tests, I will create an array of tests from each local function that will be in this function file. Now one by one, I will add local function to this file. Now I will create a setup and teardown code in this test file. These fixtures are shared across the test file. In this example, the file fixture functions will create a temporary folder and set it as the current working folder. They will also create and save a new figure for testing. After tests are complete, the framework reinstates the original working folder and deletes the temporary folder and saved figure. In this example, a helper function will create a simple figure that is a red cylinder. In a more realistic scenario, this helper function code is part of the product under test and is computationally expensive, thus motivating the intent to create the figure only once and to load independent copies of the result for each test function. For this example, however, I will create this helper function as a local function to access properties test. Note that the test array will not include this function because it does not start or end with the word test. So the create figure function is the one in which I will create an axis with a red cylinder in it. And this function will look like something like as shown on the slide here. So it is nothing but a simple function where I am creating a figure and I am creating an object with face color 100, that is red, which is nothing but a cylinder. I will create the setup and teardown functions of a file test fixture setup once and teardown once respectively. These functions take a single input argument test case. This is automatically generated by the unit test framework and passed to these functions. This test case object contains a test data structure that allows data to be passed between setup functions, all the local test functions, and teardown functions. In this example, the test data structure uses assigned fields to store the original path, the temporary path, and the figure file name. In the setup once method, I will store the original working directory path and then change the working directory to some temporary folder. Then I will create a figure in this folder by calling the figure function. In the teardown once method, I will delete this temporary folder and clear the figure with it. After that, I will restore the working directory to the original working directory. Now I will create fresh fixtures. The difference between the file and fresh fixtures is that fresh fixtures are function level setup and teardown code that runs before and after each test function in your file. In this example, the functions open the saved figure and find the handles, which I will come back to it in later videos. After testing the framework, it closes the figure. You must name fresh fixture functions setup and teardown respectively. Similar to the file fixture functions, these functions take a single input argument, that is the test case. In this example, these functions create a new field in the test data structure that includes handles to the figures and to the axis. This allows information to pass between setup, test, and teardown functions. I will create the setup and teardown functions as a local functions to the axis properties test. I will open the saved figure for each test to ensure test independence. This is done in the setup function and the figure is closed in the teardown function. Now I will create the local functions that will be included in the test array. So I will name these functions with keyword test at the beginning or at the end of the function name. Similar to setup and teardown function, individual test functions must accept a single input argument, that is the test case. Using this test case object, we can verify, assert, assume, and create fatal assertions functions. The test default x limit function verifies that the x limits are large enough to display the cylinder. The lower limit needs to be less than -10 and the upper limits needs to be greater than 10. These values come from the figure generated in the helper function, a cylinder with a 10 unit radius centered on the origin. This test function opens the figure created and saved in the setup once function, queries the axis limit and verifies that the limits are correct. The qualification functions, that is verify less than or equal and verify greater than or equal, takes the test case, the actual value, the expected value and the optional diagnostic information to display in case of failure as inputs. The second function, that is the surface color test function, accesses the figure that you have created and saved in the setup once function. Surface color test queries the face color of the cylinder and verifies that it is red. The color red has an RGB value of 100. The qualification function verify equal takes as inputs the test case, the actual value, the expected value, and the optional diagnostic information to display in case of failure. Now the access properties test.m file is complete with the main function, file fixture functions, fresh fixture functions, and 2 local test functions, and I'm ready to run the tests.
How to write setup and teardown functions, or how to write fresh fixtures and file fixtures. So for example, consider this one. So I have a access properties test. Basically this is a test function that will test whether the figure has a sufficient X limit and the cylinder that is drawn in the figure is red in color. So it will perform 2 tests. So basically I have an access property test, that is the main test function, that will, in this it will create all the test arrays, test array of all the functions. So before I move on, there is a helper function in this. The helper function, as I discussed before, is the create figure that will create figure whenever it is called. So basically it will create a figure and then it will create a red colored cylinder inside it. Now let's start with the file fixtures. So file fixture are something that, as I discussed, are something that is called only once for each file. So it has 2 functions, setup once and teardown once. So basically there is in the setup once we pass this test case object. So using this test case object, I'm going to first create a temporary folder and then I will change the working path to that temporary folder. So code for that is written something like this. So I'm going to create a inside the test case there is a test data, and inside that I will create a original path field name where I will pass the current path, and then I will create another field that is temporary folder where I will create my own temporary folder. Now I will make this directory and I will change to this directory as my current folder. Then I will create and save a figure. So again in the test data I will create a field called figure name where I will create some temporary figure. This temporary figure will be created from the create figure function and it will be saved there in the temporary folder. Now I'm going to close this figure. Again similarly in the teardown once function I will delete all these nonsense things that I just did in the setup thing. So I will delete the figure, I will delete the I will move to the original path and I will delete the temporary folder. So these are the 3 things that I have done here. Now in the fresh fixtures are something that is called once for each test function. So here we have a setup function. Again test case object is passed. So as you can recall, the test case is something that is passed throughout this file and we can use it to manipulate and pass data. So inside this test data in the figure I'm going to open the figure that has been stored in the temporary folder, and then I'm going to find the access for it. And in the teardown function I will just simply close the figure. So remember these 2 will be called before and after each test function. Now let's move on to the test function. So the first test function is test default X limit. Again remember that as my function name starts with test, so this will be included in the test array. So again here I have passed test case as an object. So inside that I'm going to take the access object and I'm going to take the limit. And using the qualification method, that is the verify less than or equal to, I will check whether the limit is less than or equal to -10, and then using another qualification method, that is verify greater than or equal, I will check whether the upper limit is greater than or equal to 10. So this will make sure that our figure is large enough to hold our cylinder. Now in the second test I'm going to check the surface color. So it's a surface color test. So here I will again find the object and I'm going to find the axis and I'm going to find the surface. Now I'm going to take that surface color and I'm going to verify whether it matches with the red color or not. If it matches with the red color, then it has passed the test case, otherwise it has failed. Now let me run this test. So I'm going to write results equal to run tests, and I'm going to run this test, that is the access properties test. So basically there are two test cases in this. Let's see what the result is. As you can see, in my current folder a temporary folder has been created, and inside that it will create some file. So this is just a warning, just ignore, as my computer does not support it. So as you can see, a figure has been opened with a red cylinder in it. Now it is continuously opening and closing it 2 times, as there are 2 test cases. So as you can see that 2 test cases have passed, and the total time it take was around 25.7241 seconds. So this was a small demonstration on teardown and setup function in function-based unit testing.
In this section, I will talk about some additional options that are available for the function-based unit testing.
Basically, fixtures are something you can use to replace or handle setup and teardown function. Fixtures handles action like changing current working folder, adding a folder to the path, creating a temporary folder, and suppressing the display of warnings. Instead of manually coding these actions in the setup once, teardown once, or setup and teardown functions, you can use these fixtures. Here, by just modifying the setup function as shown in the code snippet on the slide, you can achieve this. The fixture shown in the code that is in the test case.apply fixture class stores the information necessary to restore the initial state and performs the teardown action on its own. So the fixture is called with something like test case.apply fixture, and the path is temporary folder path is added to it, means it creates a temporary folder path, and now the same fixture is again used to change to that temporary folder path. At the teardown call, it will automatically change the temporary folder back to the original working folder. There is one additional feature that I did not cover, that is the test logging and verbosity one. That is used in the test case.log method. So by default, when running the test, these are active and can be modified when running the test and can be easily understood, hence it is not included here. Moving on, another feature just like script based unit testing is a suite creation. Calling function based test returns a suite of test objects. Test selection from this suite can be done using the testsuite.fromName method. This is similar to the script based unit testing, and by just passing the name value pair, you can select the test you want to perform. The code of it something looks like this. Again, similar to script based testing, there is a selector that is based on the name, and then using the testsuite.from file, I pass the name value pair of name and triangle, or I can use from file with passing the selector. So both ways work from him. All these 4 ways are also valid in this case of function based unit testing as well. Last option that I want to discuss is the test runner customization. This is the way the frameworks runs a test suite. With this, you can decide not to produce output on the command window, or you can run test in parallel using run in parallel method. You can add plugins to the test runner using the add plugin method. The example for the same is shown here. Here, the first line of code, I decided not to throw output to the command window, and in the second line, using the suite created, I am executing the whole test suite using the runner configuration. So the code looks something like this. So first I created the runner configuration where I told him with no plugins, that means that there will be no output thrown on the command line, and using this runner I am going to run my suite. So the suite will be run and the results will be stored in the results variable. Apart from script based and function based unit testing, there is also a class based unit testing. In this section I will cover the class based unit testing. A simple test class definition looks something like shown on the slide. When defining the test class, the class must inherit from the Matlab unit test case and should contain a methods block with the test attribute passed as an argument as shown in the code snippet. The method block contains functions. Each of these functions will be a unit test. Under this method block, as I said before, unit tests are defined. Each of these unit tests will be contained inside the method blocks. The function must accept a test case instance as an input. In these function or unit tests, qualifications are used for comparison or for passing or failing a test. Qualifications are methods that are there for testing values and responding to failures. There are like 4 types of qualification. First is the verification, which is used to produce and record failure without throwing an exception. This allows running of remaining tests to completion. Second is the assumption. This is a qualification that is used to ensure that a test run only when certain preconditions are satisfied. However, running the test without satisfying the precondition does not produce a test failure. So what happens is that when an assumption failure occurs, the testing framework marks the test as filtered. Third is the assertion. You can use this qualification to ensure that the precondition of the current tests are met. And the fourth and final one is the fatal assertion. You can use this qualification when the failure at the assertion point will make the rest of the test method invalid or basically pointless. The Matlab unit testing framework provides approximately 25 qualification methods for each of these type of qualification. I will cover these 25 methods in the later video. Now let me give you a small demonstration on how to use class-based unit testing. In this section, I will revisit the quadratic solver example and see how to write test cases using class-based testing. This is the function that I am going to test. It's a quadratic solver that takes in the coefficient a, b and c and solves the quadratic equation of form ax squared plus bx plus c equal to 0. The function will return the 2 roots in form of a numeric array. Here is how the solver test class definition will look like. This class is derived from Matlab unit test test case. Now I will create 2 functions to test for real solution and to test for an imaginary solution. First, with the real solution, I created a test real solution method under the methods blocks, and this will verify that the quadratic solver returns the right value for the real solutions. I will use the equation x square minus 3x plus 2 equal to 0 and pass the coefficients of 1, minus 3 and 2, and I will be expecting a return of 1 and 2 as an expected solution. Second, I will test for the imaginary solution. I will create test imaginary solution where I will pass the coefficients 1, 2 and 10 pertaining to the equation x square plus 2x plus 10 equal to 0, and my expected solution will be minus 1 plus 3i and minus 1 minus 3i. When using a class-based unit test. So the quadratic solver function you have seen already before in this video. It takes 3 input arguments a, b, c for solving the equation ax square plus bx plus c equal to 0. Now I will directly jump to my unit test class, that is a solver test class. So basically this class is an inheritance of Matlab unit test case class. So I'll quickly go through it once. So basically under the methods test function test block, I'm going to define my 2 test functions, that is the test real solution and test imaginary solution. In the test real solution, using the verify equal qualification, I'm going to compare my actual solution and the expected solution. I'm using the verify equal qualification. I'm going to test my actual solution with the expected solution. If both of them match, then my test case has passed. And I'm going to call the run method, and into the run method I will pass my class name without any colon, without any quotes. So this will take the class and it will execute the 2 local functions in it. So as you can see, both the functions have passed and it took approximately 0.019 seconds to run it. So basically the test array is created from all the test functions that are inside the methods test block. The test array is created from those functions. So this is like a small demonstration on how to use class-based unit testing. Building on the class-based testing, I will be expanding the test class by adding the class level and method level setup and teardown functions. Write method level setup code and class level setup code in a class-based unit testing. So first I will start with the method level of setup code class file looks something like this. So here I have taken the example of figure properties test. So here I have a method for test method setup. So this is like a method section, and inside that I will create my function using create figure, where I will pass the test case object, and inside the test case I will create a figure. Similarly, for TearDown function, I will create another method block with methods test method TearDown block, and here I will close the figure by using the close figure function. So under the blocks method test, all my test cases will be there. So basically this is how a method level setup and TearDown function looks like. It is not recommended to write TearDown function like this. It's better to add a TearDown. It is better to call a TearDown function by adding a TearDown function, like I will show you now. So the second way of writing a setup and TearDown code is having a class level thing. So in this bank account test class, so I have written a class level setup and TearDown code. So inside the method block of test class setup, I have created a function that is add bank account class to path function. So here I am creating a temporary path, say p equal to path. So I will call the TearDown function here itself by calling the add TearDown function, and I will pass the @path and p to it. It will remove the path from the Matlab path. So after that I have added my path to the Matlab path, and inside the method test block I have all my local test functions. Test constructor not enough inputs, then test deposit, test withdraw, test notify insufficient funds, and all those kind of things. So all my test function comes under this methods test block, and my only setup function comes under the methods test class setup. So as you can notice, there is no requirement for writing a separate method block for TearDown function like we did in the previous class. So these are the two ways you can write setup and TearDown function for class. And in the next video I will continue with the remaining topics. So until then, please subscribe, and thanks for watching.